Hey guys, so today we're going to begin or sort of continue our discussion of gases. So we kind of changed gears a little bit from the last chapter, stoichiometry. We're going to spend this chapter looking at the behavior of gases, and then in the next chapter kind of bring back in stoichiometry and look at how the two kind of interact with each other. So when we look at gases, or we describe a gas, again from the previous notes, you know, we're going to assume that it behaves as an ideal gas, even though it really isn't. There are really four criteria that we need to look at or know in order to know everything about that gas. So the first thing we can use to describe a gas is the pressure of the gas. Okay? So I'm just going to write the abbreviations. We abbreviate pressure typically with a capital P. The next thing is volume, which we'll abbreviate with a capital V. The third thing is temperature, we'll abbreviate with a capital T. And the last is the number of moles of gas. So that is how many gas particles we have there. And we'll abbreviate number of moles with a lowercase n. And so the PV and T are pretty self-explanatory, but you need to remember that the lowercase n stands for number of moles. Okay, so we can go through and kind of make sure we know what each of these mean. So volume is the amount of space something occupies. So temperature is a measure of average kinetic energy. So it's related to the motion of the particles. Okay, you all know that a mole, or hopefully you know, the mole is the SI unit for amount. Okay. So then the one that might be more new to us is pressure. So pressure is defined as force per area. Okay, so basically how much force are we applying over a certain unit area. So we know for our previous descriptors of gases, we're familiar with the units. Volume, we use liters or milliliters. Temperature, we use Fahrenheit, Celsius, or Kelvin. The mole is our unit there. But for pressure, we have a new unit. And the unit for pressure is a Newton. We abbreviate that with a capital N. Okay, so a capital N is the unit newtons. A lowercase n is the abbreviation for the number of moles. So it takes you through kind of where that unit comes from. You can read that on your own. One thing that is important to think about here is the third bullet, where it says the same force applied to a smaller area creates a greater pressure. And so the example in the textbook talks about a ballet dancer who stands flat on their feet, and there is a certain amount of force applied to the bottom of their feet, but then when they stand on the end of their toes, the same amount of force is being applied, but it's being applied to a much smaller area, so they feel a greater pressure on their toes. So even though the force is the same, the area over which the force is applied changes when they get on their toes, so they feel a greater pressure there. Okay? So when it comes to a gas, we obviously don't look at standing flat on your feet or on your toes looking at pressure. The three factors that determine the pressure of a gas is the volume of the container the gas is in, the amount of space that the gas has to occupy, the number of moles of gas, so the amount of gas, and then the temperature of the gas. Okay. A couple of things, excuse me. One thing that we use quite a bit, a phrase that you've probably heard before, is atmospheric pressure. So atmospheric pressure is a descriptor of gas pressure. So atmospheric pressure is just the sum of all the pressures of all the gases in the atmosphere. And it changes from day to day slightly based on the weather. Hey, sorry about that, my phone rang. Anyway, I think I got off the definition of atmospheric pressure there. So that's something that we'll talk about quite a bit. As you know, there's gases all around us, and there are many different types of gases surrounding us, so rather than describing the pressure of each individual gas, we just kind of lump it together and talk about the pressure of the atmosphere above us. Okay? So for number 19, it asks, why did the can collapse in the demonstration? So if you're watching this as a full-time virtual student, you'll want to go click on the other video link that I posted to the YouTube video and you'll see the demonstration. If you're an in-person student, you'll see it in class. But either way, after you watch the video or see the demonstration, you'll learn or hopefully know that the can collapses because as you decrease the temperature, when you stick it in the ice water, you decrease the temperature of the gas inside the can, which greatly decreases the pressure. Okay, so that decrease in temperature causes a decrease in pressure, which then causes the can to collapse in on itself. Okay, so before we can get to the calculations, a couple of other just kind of facts and things we should know here. A barometer, hopefully you know what that's used for. It's used to measure atmospheric pressure. So when you see the barometer readings on the weather in the morning, you know what that is. Kind of just a person you should be familiar with. Torricelli was the person who first invented the barometer. So Evangelista Torricelli, you can just learn his last name, Torricelli, was the first person to actually develop a working barometer, and there's many applications that we use from that today. So because we're on either the hybrid or the full-time virtual model this year, we really won't look at reading barometers this year, so we can just skip that whole little section there. So that takes us down to where we're going to start talking about what we call standard temperature and standard pressure. So before we talk about our standard temperatures and standard pressures, we need to know why we need these standards. We've got to have these standards so we can compare different samples. Okay, so if we have one sample at, let's say, a temperature of 75 degrees Celsius and another sample at 25 degrees Celsius, the samples could be the exact same, but they might behave differently because they're at different temperatures. So we set these standard temperatures and pressures so we can easily talk about and compare different samples of gas. So the standard pressures, the different units, are written out here. So we have quite a few different units that will measure, that we'll use to measure pressure, and there are quite a few. The most conventional and most common unit for pressure, and I left off at the top, we didn't discuss it there, so if you want to go back and write them in up there, you can. The 4 units we'll look at, or you can just look at them down here. Anyway, the most common is atmospheres, okay, so ATM. So as you could guess, 1 atmosphere is pretty close to the normal atmospheric pressure at sea level on a normal day. It can vary slightly from there. Okay, we also have other units, one known as torr. Okay, so 760 torr is equal to 1 atmosphere. We also have another known as millimeters of mercury. So mm is millimeter, Hg is mercury. And that is a measurement from the barometer that we can look at as where that comes from. So 760 millimeters of mercury also equals 1 atmosphere. Then the final unit of pressure that we'll use is a Pascal. So PA stands for Pascal, but we'll often see it written as kilopascals, KPA. But we can also easily convert from kilopascals to pascals. And so these are 4 new conversion factors that you need to be aware of and know. Okay, so if I ask you to convert from one to the other, you'll be able to apply these. Just like 12 inches is 1 foot, 760 millimeters of mercury is equal to 1 atmosphere. And so those are our standard pressures, but we use this thing often referred to as STP when we describe gases, and that's very important. So STP stands for a standard temperature and pressure. Okay? So our standard pressure up here are any of these options, okay? Because they're all equivalent to each other. We can choose any of them. We typically say our standard pressure as 1 atmosphere because it's a nice easy number to remember. And our standard temperature is 0 degrees Celsius. So anytime a problem describes a gas at STP, that's telling you the gas is at 0 degrees Celsius temperature and a pressure of 1 atmosphere. Or it could also be a pressure of 760 millimeters of mercury because those are the same thing there. So there are a couple of practice problems here that I'll leave for you to do on your own. Just using dimensional analysis, make sure that you are able to convert from one unit to the other. Make sure you can convert from 1.75 atmospheres to kPa, millimeters of mercury. That should be pretty straightforward. The answers are written down there below just to make sure you get the correct answer there. And those are numbers you want to go ahead and commit to memory. Okay. So as we go over to the next page, we really now want to begin what is the whole focus of this chapter, looking at what we refer to as the gas laws. So everything we've done so far is just kind of a build up to get to this point to be able to calculate these things we're going to look at. Okay, so gas laws are kind of the generic term for the mathematical relationships between the different variables that we use to describe gases. So if we think about what we use to describe gas, pressure, volume, temperature, and number of moles, so the gas laws are the mathematical relationships that exist between these different variables. Okay, so there's three that we'll look at, then there'll be a final one that will kind of bring those three laws together. So this is probably a review from either 8th grade physical science, or if you took physical science at high school level. But anyway, it won't hurt to review here. Okay, so Boyle's law, what that tells us is that, and I'll abbreviate here, at a constant temperature and number of moles, pressure and volume are inversely related. So if they're inversely related, that means as one increases, the other decreases. So if you think about that, just kind of reason through it there, think about if you have a container that has gas in it of a certain volume, and you decrease the volume, you make the volume smaller, the pressure will increase. Okay, so that should make sense to you logically. And we can write it in terms of an expression like this: pressure times volume equals K, which is a constant. Okay, so if pressure times volume always equals the same number, if pressure goes up, volume has to go down to compensate. Or if volume goes up, increases, pressure also has to go down. Okay, so that is an inverse relationship. So in terms of a formula, it's typed out for you here. Okay, so all these gas laws really are used to describe a change. Okay, so you have a gas at a certain temperature, pressure, and volume. Then you're going to change one of those things. We're going to calculate how the other variables react to that. Okay, so pressure 1 times volume 1 equals pressure 2 times volume 2. Okay, so P1 V1 equals P2 V2. You'll also see it written quite often: initial pressure times initial volume equals final pressure times final volume. So let's look at this problem here. A balloon filled with helium has a volume of 500 milliliters and a pressure of 1 atmosphere. The balloon is released and reaches an altitude of 6.7 kilometers, where the pressure is 0.5 atm. If the temperature remains the same, what volume does the gas occupy at that height? So if you read through that, you see we have an initial situation where I have a initial volume, an initial pressure, then I have a final pressure, and I'm looking for a final volume. Okay, this distance up in the sky is irrelevant. We don't need to know that. Okay, so I have my formula: P1 V1 equals P2 V2. So I can plug in here. My pressure 1 is 1 atmosphere. My volume 1 is 500 milliliters. My pressure 2 is 0.5 atmospheres. And then my final volume, I don't know. Okay, so you can pretty easily do the algebra here, divide both sides by 0.5. So I'll go ahead and show you on here what it looks like. So I have V2 equals 1 atm times 500 milliliters divided by 0.5 atm. So that cancels. When you type it in numerically, you get 1,000. In the units you're left with are milliliters. So our answer here is 1,000 milliliters. So the question might come up at some point: if I have several different units that I can report volume in, such as liters or milliliters, and I have several units that I can report pressure in, atmospheres, kilopascals, etc., does it matter which one I use for these calculations? And the answer is no, as long as they match. So what that means is, if pressure 1 is in atmospheres, pressure 2 has to be in atmospheres. So let's say, for example, I gave you pressure 1 in millimeters of mercury. Then you have two options. You either convert pressure 2 to millimeters of mercury so it matches, or you convert pressure 1 to atmosphere so that it matches. So it doesn't matter what units your pressure and volume are in, as long as they match each other. Okay? So that is Boyle's law there. So the next law we'll look at is Charles' law. So Charles' law states that at a constant pressure and number of moles, volume and temperature are directly related. So that means as one increases, the other also increases. As one decreases, the other decreases. Okay? So we can write that here as direct. So one important thing to note here, and from this point forward with the calculations, in Charles' law, in any of the laws, temperature has to be reported in Kelvin, not degrees Celsius. So we can very easily calculate Kelvin as our temperature by simply taking degrees Celsius and adding 273. So anytime you're given a temperature in Celsius, you want to go ahead and add 273 to it to convert it to kelvins. And the reason we do that is to alleviate any issues we might have with a negative number. So you can have a negative temperature in Celsius, but you can't have a negative temperature in Kelvin, because absolute zero, the lowest possible temperature, is 0 Kelvin. That's where all molecular motion stops. So we don't have to worry about dealing with negative numbers with the Kelvin scale. So if you look at a few of these, 0 degrees Celsius is equal to 273 Kelvin. 100 degrees Celsius is equal to 373 Kelvin. Okay, negative 273 Celsius is equal to, how do you do that one there? Okay. So if we add 273, we get 0. So can we have 0 Kelvin? Well, in theory, we can have a absolute 0, but in practice, we won't see that. Okay. So you can have 0, just not a negative number there. So then for these, where you're given Kelvin and asked to convert to Celsius, you would just subtract 273 there. So that's a number that you should be familiar with and know we'll do that quite often. So let's check out an example now. A sample of neon gas has a volume of 752 milliliters at 25 degrees Celsius. What will the volume be at 100 degrees Celsius? The pressure is constant. Okay? So let's go ahead and label what I have. I have an initial volume, I have an initial temperature, I have a final temperature. Okay? So I can use the Charles law formula, V1 times T2 equals V2 times T1. It's kind of difficult to remember like that. The way I prefer to write it is V1 over T1 equals V2 over T2. So this formula and this formula are the exact same thing. They just cross multiplied to get that one, but I prefer using this one. Okay, so I can just plug in this formula here. Volume 1 is 752 milliliters. Temperature 1 is 25 degrees Celsius, but I'm going to have to add 273 to convert to Kelvin. So I can take 25.0 plus 273, it's going to be in Kelvin, equals, I don't have a volume 2, I'm trying to solve for that. And then my temperature 2 is 100 Celsius, I convert that to Kelvin, 100.0 plus 273. Okay. So then you can pretty easily add those two on the bottom, cross multiply, solve for V2, and you'll get that V2 equals 941 milliliters. Okay? If you cancel out your units as you should see that you retain the units of milliliters. But you should also know that whatever units you start with for V1, V2 has to end up in the same units because units are retained there. Okay? The big mistake on those types of problems is to forget to convert to Kelvin there. Okay? And sometimes you'll see that it's more important than others, but it's good to go ahead and get in the habit now so you don't have to worry about it. Okay? So, Gay-Lussac's law is our last of the three different gas laws that we'll look at. So it states that at a constant, volume and number of moles, pressure and temperature are directly related. So if you think about the common time you see this is with your tire pressure. So in the summer when it's 100 degrees versus in the winter when it's 0 degrees, the pressure of the air in your tires can vary greatly. As it gets hotter, the tire pressure increases. As it gets colder, the tire gas pressure decreases. So the formula here is P1 T2 equals P2 T1. Again, I prefer to write it as a fraction. So P1 over T1 equals P2 over T2. So those are the same thing. One's just cross multiplied to get the other form, but I prefer this form right here. So we have a problem here. A sample of helium gas has a pressure of 1.2 atmospheres at 22 degrees Celsius. And what Celsius temperature does it need to be to reach a pressure of 2.00 atmospheres, assuming a constant volume? So the first thing we ask ourselves is, do we have pressures that match? We do, so no conversions are required. And we have a temperature in Celsius that we want to convert to Kelvin. So I have P1 over T1 equals P2 over T2. So I have 1.20 atmospheres divided by 22 plus 273 Kelvin equals 2.00 atmospheres over T2. Okay? So when you cross multiply and get that, your answer is not going to be in Celsius. Okay? Whatever temperature you use initially, it will have the same units as your final temperature. So if you get your answer in Kelvin, you'll need to subtract 273 to get your temperature in Celsius. And we have to do that because the problem explicitly asks us what temperature in Celsius. So don't forget when you get your answer here to subtract 273. And so all those gas laws, the three that we looked at, are great and all. We kind of went through them quickly because we really very rarely use those. What we'll typically use is what is described on the next page. It's called the combined gas law. So the combined gas law simply combines the three gas laws that we just looked at. So we'll just write the formula rather than a definition in words. The formula is pressure 1 times volume 1 over temperature 1. Pressure 2, volume 2 times temperature 2. Okay? So if we have our initial conditions and we change one of them, this formula allows us to calculate how those variables interact with each other and change there. Okay? The only rules, if you will, to using this formula are that the pressures have to be in the same units, the volumes have to be in the same units, and the temperatures have to be in Kelvin there. Okay? So we could also work all of the previous problems that we looked at using the combined gas law. So look how I might do that. So let's look at this problem right here. Okay, so this problem, we used Charles' law the first time. Okay, so but if I look at the combined gas law, P1 V1 over T1 equals P2 V2 over T2. I don't have a pressure here. So when you're using the combined gas law, if you don't have a pressure mentioned in the problem, you assume that it stays constant. So if it stays constant, think about plugging a 1 in here, for example. It's not going to affect the answer. So as long as it's constant, you can cross it out. So if I cancel those terms out because they don't change, now I have a version of Charles' law. So that's why it's easier just to always start off with the combined gas law, then cancel out whatever terms you happen to not need there. So let's look at an example here together. A volume of gas is 27.5 milliliters at 20 degrees Celsius and 0.974 atmospheres. What will the volume be at 15 degrees Celsius and 0.99 atmospheres? Okay, so we're taking our sample, we're changing both the temperature and the pressure, and trying to calculate the final volume. So we use the combined gas law here. So my P1 is 0.974 atm. My V1 is 27.5 milliliters. My temperature is 22 Celsius that I'll convert to Kelvin. It's going to equal my P2 is 0.993 atmospheres. My volume 2, I don't know, that's what I'm trying to solve for. And then my temperature 2 is 15 Celsius that I will then convert to Kelvin. So before you do the math, you want to check some things. Make sure your units are going to line up and cancel out. You have atmospheres and atmospheres, so we're in good shape. No need to convert. We have Kelvin and Kelvin. We have milliliters here. So my final answer, V2, will also come out in milliliters. Okay, so now you can solve for V2. It's pretty straightforward and simple algebra there. Okay, so let's look at one more together. 700 milliliter gas sample at STP is compressed to a volume of 20 milliliters, and the temperature is increased to 30 degrees Celsius. What is the new pressure of the gas in pascals? Okay, so this question is a little bit different. So we have an initial volume but we don't have an initial temperature or pressure. It just tells us STP. But we remember, hopefully, that STP tells us it's 0 degrees Celsius and that it's 1 atmosphere. So we can plug in 1 atmosphere here and we'll be in good shape. But the final answer asks me for it in pascals. Okay? So that's going to be a little bit of an issue. So I have a couple of options for how to deal with that. So my first option would be to take my initial pressure, if I start off with ATM, and just go ahead and convert that to kilopascals. Okay? And I really don't need to do a conversion there because I know that 1 atmosphere is equal to 101.325 kPa. So instead of writing 1 atmosphere, I can just write 101.325 kPa. And that's the first option, I think the best option. The other option would be just to go ahead and do the calculation with 1 ATM. And then your final answer, your P2, will come out in ATM. Then you can do the calculation to convert from ATM to kilopascals, and then from kilopascals to pascals. Okay, so go ahead and try that one on your own. Plug it in this formula, make sure you can get the correct answer there. Okay. So we'll use that formula, the combined gas law, quite a bit. One other formula that we'll use is called Dalton's law of partial pressures. So all Dalton's law of partial pressures is a very simple concept, probably the easiest calculation or concept to look at the whole year. So Dalton's law just tells us that the total pressure of a gas is equal to the sum of all the individual pressures, or we call them partial pressures. Okay. So you have the formula there. So pressure total equals pressure 1 plus pressure 2 and so on. So all that means is, we can come up with an example down here. If I have a mixture and then I have nitrogen, oxygen, and hydrogen gases, if the pressure of nitrogen is 1 atmosphere, the pressure of oxygen is 3 atmospheres, the pressure of hydrogen is 2 atmospheres, and they're all in the same container, and I want to know the total pressure of the container, you can just add all the pressures together there. So the total pressure of that container would be 6 atmospheres. Okay? And I would call this the partial pressure of nitrogen, okay? Because nitrogen only makes up a part of the total pressure. So each individual gas has a partial pressure, the whole container has a total pressure. Okay? So that's a very straightforward thing there. So then the last thing that we'll look at here is an application of Dalton's law that deals with when we collect a sample of gas that is above water. Okay? So there is a very common method that we'll look at in the lab for collecting a gas above water. The only issue is, as you might can imagine, let's just draw an example here. So let's just say that's my water level. Then I have an inverted tube or graduated cylinder here. And I can say I have a hose that's going to pipe in the gas. So as the gas comes in, it will force the water out of the tube, and I can measure the amount of gas I have in the tube. The only issue with this technique is, that's referred to as collecting a gas over water that we'll do in lab, is that water also can be converted into a vapor, into a gas. So if, let's just say, I'm adding hydrogen, okay, adding hydrogen gas to the tube, all of the pressure in the tube will not result from the pressure of hydrogen. Some of the pressure will result from the evaporated water, so we have to account for the partial pressure of water there. So we can do that by simply subtracting that out. Okay, so we will have tables, and you will be given what the partial pressure of hydrogen is, or we typically, or not, excuse me, let me back up. What the partial pressure of water is. So we typically call that the water vapor pressure. So based on the temperature, we can look at a chart and get the water vapor pressure. So let's just say, for example, that we did this measurement and we found the pressure of hydrogen to be 3.0 atmospheres. Okay, but then we took the temperature, went to our chart, and we found that the pressure of water was 0.5 atms. This is the water vapor pressure. So in that case, the pressure of hydrogen is really not going to be 3. We need to label that the total pressure, because we just measured the pressure inside this tube and we assumed it was all hydrogen. We didn't account for the fact there was some water vapor present. So in this situation, we'll want to subtract off the partial pressure of the water, and we'll get the pressure of hydrogen as being 2.5 atm. Okay. So that was a little bit complicated. I made that harder than I should have. I apologize for that. The main thing is just keep in mind when we get to lab and do this, we will need to account for the water vapor pressure, and I will discuss it more then. And so the last thing that you can do, and I won't do this with you, you can do it on your own, is use this chart on the next page to kind of condense your thoughts for all the different gas laws. So for Boyle's, Charles, Gay-Lussac's, and combined gas law, you can write in the equation. For these three, the proportion that exists, what is constant, and then you can come up with your own example here. So you can very easily, for all these, come up with your own situation. So for Boyle's law, you might say, I have an initial pressure of 5 atmospheres, an initial volume of 50 milliliters. If volume is increased to 1,000 milliliters, what will the new pressure be? So come up with those and solve it on your own. And that's a nice little way to combine your thoughts for that. Okay? So those are the basic calculations that we'll do with the gas laws. We really haven't done any chemistry or chemical reactions. All we've done here is looked at how to calculate how different variables of a gas react to change. So if we change pressure, how does volume react? Or if we change temperature, how does pressure react? So we'll practice this for a few days, and then we'll come back and take this forward by using these calculations to solve problems involving chemical reactions. Okay? So I hope you have a good rest of your day. If you have any questions, feel free to send me an email.